I am K.S. Narayan. I welcome you all on behalf of IIT Alumni Center, Bangalore, for the 86th webinar. We have been conducting these webinars online since April 2020. It's really been a successful series, and in case if you have missed some of the lectures, you can find our previous webinars on YouTube. Today I'm joined in here with Professor Abha Mishra of Indian Institute of Science. We are representing IITACB. Today's seminar is on highlights from surveys of galactic star clusters using AstroSat. AstroSat is India's first dedicated space observatory, which was launched by ISRO in 2015 and has been a landmark achievement in our country's space exploration journey. With its unique capability for simultaneous multi-wavelength observation, AstroSat studies celestial sources across X-ray, optical, and UV bands, covering large energy range from near and far UV to X-ray regimes. The UVIT Imaging Telescope on board AstroSat has been producing exceptional far UV images, enabling groundbreaking discoveries since its inception. To go deeper into these remarkable achievements, we are really honored to have an expert, Dr. Annapurni Subramaniam, the Director of Indian Institute of Astrophysics, Bangalore. Dr. Annapurni is a very well-renowned astrophysicist whose research focuses on the star cluster, stellar evolution, and galactic studies. She has led significant UVIT surveys to study open and globular clusters with impactful publications covering blue stragglers, white dwarfs, sub-dwarfs, and planetary nebulae. She earned a PhD from IIA and has made substantial contributions to the fields of galactic structures, stellar populations, and star formation. Her achievements were widely recognized with the prestigious Vigyan Shri Award among many others in 2024. She has been an active member of the International Astronomical Union and really is an inspiring role model, particularly for women pursuing STEM careers. She continues to shape the future of astrophysics. And along with her, we have today's session being moderated by Dr. Prateek Sharma, a renowned astrophysicist and professor at Indian Institute of Science. He's a graduate of IIT Bombay, and he's done his PhD from Princeton University. Dr. Sharma has an illustrious career, including a NASA Chandra/Einstein Fellowship at UC Berkeley. His research spans galactic atmospheres, black hole accretion, MHD turbulence, and cosmic ray acceleration. He is a recipient of several prestigious awards, including the Swarna Jayanti and the Humboldt Fellowship. And he's also the Fellow of Indian Academy of Sciences. So it's going to be a great webinar today. I encourage the audience, the participants, to engage in this discussion via the Q&A box and not the chat box. Okay. So over to you, Annapurni.
Thank you. Thank you, IITAC and the organizers for inviting me to this talk. Am I audible? Can you hear me, right?
Yes, yes, very audible. Yeah.
Okay. So, yeah, thanks again. I shall share my screen and then start the presentation. So are you able to see my screen?
Yes.
And
Yes,
is it
yes.
screen,
Yeah.
right? Okay.
Yeah.
All right. So thank you for coming over to listen to me. And so this presentation is focusing on the highlights from 2 surveys of galactic star clusters using AstroSat. So in this talk, I would be talking about, on the first half, I'll be describing to you about the space mission which is like very unique with 5 payloads on in this single mission. It's therefore it's called an observatory. It's not a single instrument, and this is the first such observatory planned and launched by ISRO, and it is operated, and it is completing 10 years in orbit in September. So it's really a remarkable achievement, and a lot of learning has gone through this. So I would present in the first half the making of UV. I mean, basically, I was the calibration scientist on the UV Imaging Telescope, which is basically the 2 yellow tubes on this. And I would primarily focus on the development and calibrations, and how do we make sure that it is doing what it is supposed to do in space. And that would cover the first half of my talk. And then in the second half, I would talk about the science which I have done using this instrument, and what is the impact it has made to the international scene. So that is the format. And let me, before I go on, dwell into the AstroSat mission, I would like to give a brief overview of the institute where I am the director. Sorry. So this is, I'm with Indian Institute of Astrophysics. This is an autonomous body under the Department of Science and Technology. It traces its origin to an observatory set up in Madras, Chennai in 1786. And it is actually established as the Madras Observatory in 1792 in Chennai. And it is there operating, doing various stuff, including observing the sun, the planets, and the total solar eclipse, etc., including the famous Machilipatnam total solar eclipse in 1868, which contributed to the discovery of helium. And there was some discussions to find out to make a find a better place for continuing observation of the sun, particularly because of the drought and various stuff which was encountered in the late 1870s. And Kodaikanal was identified as the hill station in southern India where they felt it is ideal to set up a solar observatory. So the Madras Observatory set up Kodaikanal Observatory in 1899, and in about 1930s, they shifted everything out of the Madras Observatory, and it was closed in Madras. And the observatory in Kodaikanal continued its observations and all the activities. And in 1971, the Indian Institute of Astrophysics was born as an autonomous body, and then later it moved to functioning under the DST. And the headquarters then shifted from Kodaikanal to Bangalore. And in 2020, we celebrated the 50 years of formation of IIA. But as such, as we trace our history, it's more than 200 years old in institution. So the picture on top is the IIA campus. And we have several field stations, including the Kodaikanal, which is celebrating its 125 years of operation. So that's one of the oldest observatories in the country as well as in the world. And beyond Kodaikanal, it has expanded to establish multiple observatories, including the Vainabapu Observatory in Kavlur, which is near Vellore. It is situated in Javad Hills, and it is for nighttime astronomy. So we have several telescopes out there. And we also have a Gauribidanu Radio Observatory, which observes the plasma, which is emitted by the sun. It's radio observations and decameter. So that is contributing to the daytime astronomy. But we're also trying to observe some pulsars and other objects as well. Later, due to the conditions in southern peninsula, which is affected by both the monsoons, the southwest and the northeast, there was ambition to set up an observatory in the Himalayas where the cloud coverage will be minimal, and that was established in 2000, and we are running the International Astronomical Observatory in Hanle, Ladakh for the last 25 years. And since it was established in 2000 and reaching Ladakh was a nightmare, so the condition was that the telescope is remotely operated from Bangalore. So we set up that in Hosakote campus. It's called CREST. And this campus is expanded to accommodate our space sciences laboratories as well as the mirror polishing facility for the mega science project, the TMT. So the upcoming projects being the institute is setting up a planetarium of it's a first of its kind LED dome planetarium in Mysuru, and it's going to be operated as a field station. And we also have two space capabilities. One is the AstroSat, of which I'll be talking today, and we also have delivered and are currently operating the prime instrument on the Aditya L1 mission, which is the coronagraph to study the sun. So our solar group, which is a very strong group, is behind this, and they are deriving science out of it right now, because it is completed about a year in orbiting around the L1 point to study the sun. And the 30-meter telescope project, the Indian Institute of Astrophysics is the main coordination center, and we partner with the international countries who are members of this consortium, as well as industry, to deliver the in-kind contributions from the country, which is of the order of 1,300 crore project, and of which 70% is in-kind. And we currently are working with about 20 industries, and throughout the last 10 years or so, we have worked with about 17 industries, validating them to into the production phase. So they participated over the prototyping phase, but some failed and some succeeded. And we are working with 20 of them right now for in-kind contribution. So moving on to, so this is the technology aspect with respect to the major projects. This is still ongoing, and there's a large team within India and other organizations also involved in it. Now, coming back to the AstroSat. So this is the mission, the main instruments on board AstroSat, and this is the LAC species, which is basically the large area xenon field proportional counter, which is an X-ray instrument, and CZTI is another instrument, X-ray instrument, S60 X-ray instrument. So X-ray covers from a soft X-ray range of 0.3 kV to about 80 kV, but it goes beyond that in the CZTI. So it's a soft X-ray to hard X-ray coverage is over there. And these instruments are shown here. The red one is the LAC PC, and the CZTI is shown behind this pink panel. And these are basically proportional counters, and the S60 is an imaging device with in the soft X-ray. It's like a telescope. So that is a tube out here. And the scanning sky monitor is to look at the transient sky, X-ray sky, and look at any eruptive variables in X-ray, and that's shown in green. And the Ultraviolet Imaging Telescope is shown in yellow, 2 tubes. And I'll explain why we need 2 tubes for UVIT. And this has got some a partnership within India as well as outside India. So the CSA is a partner in UVIT, and they have been responsible for the electronics, and the University of Leicester is part of S60. So mostly this is a Make in India mission, and most of it is made in the country with some components coming from outside. So this is when you start off with a major instrument development, you set out by putting out specifications. What are the overall specifications, and what would you like to achieve? And these are the targets to be achieved. And so the main parameters are shown here. Just starting from what is the kind of operation you have, imaging or spectroscopy, what kind of an optics, what is the bandwidth of optics, what is the geometric area, and what is the effective area. If you look at these two, they are the area, but then what it means is that the ratio gives you the efficiency. So it's just that you have a collective area of so much centimeter square, but then in efficiency wise, it would actually act like how much kind of an area it is. So this is basically an efficiency factor. Another important factor is the field of view, what kind of a coverage you have of the sky, the energy resolution, angular resolution, time resolution, and the typical observing time, and the sensitivity, like what kind of a faintness can you achieve. So these are target numbers were put out so that the instrumentation as well as the entire integrated system should perform to achieve these numbers. And the entire design has to look at it, and the error budget which you put it out also has to be met. it's very important in the development stage, because at each point you have to make sure that you are achieving whatever you are set out to be. And then if there are any changes and if you're not able to achieve the set out specifications, then there will be an impact on the science, and you have to immediately evaluate on the science impact of this deviation. So this is the proposed two telescopes. Now we are dealing with a far UV instrument and the near UV, the ultraviolet instrument for that matter. So what is special about ultraviolet is that the ultraviolet rays which are coming from cosmic objects, including the sun, they do not enter the Earth's atmosphere. So that's because the molecular absorption and the ozone stops it. So in the Earth, we are not receiving the UV radiation. So that's the reason you need to put out an instrument out in space. But because of the same reason, if you integrate an instrument on Earth and set it out, put it out outside, there would be molecular contamination within, and every photon, UV photon, which is entering will be absorbed well before it reaches the detector. So here, what is shown here is the pink one, which over here. I hope you can see my cursor. So this is the primary mirror, and then that gets reflected onto the secondary mirror, and the beam passes through a hole in the primary mirror to reach the focal volume. And this is where you have the filters or optical filters as well as the detector system, etc. Now, if you are allowing a UV photon to enter, it has to be reflected and then it has to pass through some material before it gets into the detector. Now, this photon can get absorbed at any point, so it doesn't give you much of an efficiency, but the most efficient way to do is to only reflect it and not let it pass through something. So we do have to pass through some windows. When you have a detector, you have to have an optical window, etc. And that window has to be crystal so that it doesn't have a transition for absorption. So that is the reason why in the UV telescope, you must have only reflecting surfaces. If there's any transmission, then the efficiency drastically gets reduced. So because of that, the far UV telescope only has reflective optics, and it gets finally absorbed in the detector. But in the case of the near UV, you have a beam splitter where it splits the beam into two. One goes to the near UV detector and the other to the visual. So the reflective beam is obviously the near UV and the transmission beam is the visual. So you have two detectors in one telescope and one detector in the far UV telescope. So that's a twin telescope basically. And so this is the actual design, and then you have to realize it in the optical bench, which is the class 100 tent in our MGQ Men and Space Science Lab in Hosokote Lab. So before we started this making of this telescope in early 2000, we did not have any clean room facility, and we actually established one by 2005, 2006. And it's not only about establishment, but also about making sure that it's contamination free and contamination controlled. So we had to draw a lot of protocols and also make sure that it is monitored. And also that molecular contamination has to be strictly, controlled in all components. So everything has to be baked to make sure that any material which gets outgassed when it is heated up should not contaminate. So everything is baked before putting in. There's a huge lot of procedure and protocol which needs to be made and followed strictly. And material used, coating used, everything has got its own protocols. So it was actually a completely new learning experience. And also there are a lot of things which you have to make, but then there are a lot of additional stuff with respect to calibration, handling, fixtures. Everything had to be designed. So all of our engineers had to design a whole lot of them and then manufacture with our local industries to make sure that you have fixtures and all the testing equipments and calibration equipments, etc. So it was like a lot of learning experience for us. Now, this is the inside of some of the pictures while it was getting integrated. And you can also see that in the process of making, you also have to make, in the case of space instruments, you need to have to go through certain specific steps. And only if you successfully complete that step, the next step is taken up. And you can't do it in a parallel way, because if anything fails, you have to go and redesign and make sure that meets the space requirement. So we had a qual model first, and then an engineering model, which is basically a mass model. And then you have to go through the vibration and so this is a mass model. It goes through the engineering model, was complete engineering, full scale mass model was made. And it was actually vibrated to make sure that none of the connections is broken, no mirrors are broken, no bolts are broken. so that it survives in the launch and in space. And then only you go into the making of the flight model. So this is we have a component levels testing, and even component level is environment tested for vibration and thermovac. And there's a vibration test for the CPU of the detector. There's a testing of the full the flight model at the lab, and the interface tests for the spacecraft, and the connector flange for the thermovac test. So there are a lot of things which you need to encounter at short intervals. You have to design, fabricate, test it, and integrate it. So it's a dedicated team of people and a lot of know-how gained in that process. And so these are the making part of the entire vacuum tank. Also for calibrations, it's an integrated system. The component level calibrations is one, testing is one, the integrated testing is another. And the cabling, the heating up, the wiring, everything has to be taken up, and also have a very meticulous planning and execution. And not too many people can get into the room because there's the contamination issues. So these are all completely new learning, but it's a major instrument as well. But it passed everything, and then finally it was delivered. And then this is the 2 tubes ready for integration onto the spacecraft interface. So this is the spacecraft interface, and it's on the vibration. It's a shaker. It shakes as per the gravity which is expected on the launch, and it is going through the vibration testing. And this is the fully thing integrated in the checkout in ISIT as part of ISRO. And this is actually the 2 tubes, and you can see this blue tube which is actually purging. That would mean that if you have a molecular contamination, it is flushed through. So this has been there all along while transporting. So transportation is also a big job because you have to make sure that the vehicle moves. It's less vibration, and the accelerometer is put everywhere, and you get the data to make sure that at any point it does not cross the acceleration. It should, it should be within the safe limit. So that's monitored all along. And then it was launched on 28 September 2015 on C30. This was from Sriharikota. And so actually it was launched on 28 September. And as you know, there are many instruments out there. So you have all these instruments. So a lot of commanding goes on because they are operated simultaneously, and they look at the same part of the sky. So you have to operate them simultaneously. So there was a sequence of powering on, because once your solar panel is out and the power is on, everything can't draw power immediately. So there's a power on sequence. When you have power on sequence, there would be certain outgassing may be there. So it was decided that the UVIT would open the doors only after 2 months. It also had its own risks because within 2 months, it'll be quite cold out in space. And it was actually like, this door has to be open. 2 doors are there. You can see this hinges there, but it has to be fully open. And you melt the kind of a frozen stuff here, so it completely opens. So this is direct commanding from the ISRAC for opening, and we did it on 30th of November. And the 30th of November means it's almost 2 months, and the actual observation starts. So what you do in the first observation is to actually look up at the part of the sky where you can actually imagine all the 3 filters of far UV, near UV, and visual. So I was tasked with coming up with the whole plan of what all things you need to do, what all things you need to prove that the instrument is working and working as per the parameters which I put it out in the first slide, right? So the specifications. I have to prove that everything is met and it's ready for science. And if it is not met, how it is not met, and how is the impact on science? So people can plan on their science. So that was my responsibility, and also to predict how it would be so that I can plan the observations. So it has to be passed to the calibration committee and then execute it. So I have to also make sure that the commanding giving is same and the filters used are same, the modes of operations are correct, etc. So this is the kind of data you get, because this is start time and end time. You see these trails. That's because there is the satellite drifts, and also there is a kind of a motion which is given so that the detector doesn't burn out. But as I said, 2 detectors sit with the near UV and visual, but at the same time, far UV is on a separate telescope. So they are the angle differently. So you can see there's about 60-degree difference between these 2. So 120 shift you can see here. And this this has to be corrected. So there's a lot of post-processing involved. And after the post-processing, you get the far UV image, and this is the first light object. And this is the near review image, and this is the spectrum. So this basically told us that everything, all the optical components in the telescope is intact, and the detector is working, and then it is to find out the parameters for which it can be converted, these images into science-ready images. That's part of calibration. So this also, like, if you can, this was a kind of a demonstration of a galaxy. So this is the signature, which is basically because of the satellite drift as well. And then the motion which is given to maintain save the detector. So if you de-drift it, the image with the help of the time-wise photon counts, you actually get this images. So this was the eye opener. This is the lower picture is the ground-based image, and this one is the image of the same object from a previous NASA mission, Galactic. And this is the image we got from the near UV filter. So you can actually see it's very nicely focused and better resolved than the previous image. So it was evident that this instrument is going to provide immense data, very good data to do very good science. So everybody got excited, and then we have been doing science for the last 9 years after the performance verification period. So I don't want to get into this very busy slide, but this is basically the kind of calibrations, and we put out several papers completing the calibrations. And this is the different filters, which tells you that on the y-axis, you can see the effective area, which would mean that this is, though it's a bigger telescope, but then effectively it works like this. And this is for the different channels, the visual, the far UV, and the near UV and the visual telescope. And so this was launched on 28th September, doors open on 30th. And observation for more than two years, we actually completed all the guarantee time, performance verification, etc. for the Indians and the instrument team. And then we started open time for proposals. And it has been done on Indian as well as international proposal time since 2017. There are many observations, many interesting work carried out from various things, but we also have the responsibility to track the health of the system and calibrate once in a while to make sure that the sensitivity is not dropping. So the science-ready images are produced well, etc. So I also carry out certain sensitivity tasks, tracking the sensitivity tasks, and and updating the CalDB, etc. So that is the operational and the calibration updates. And another important factor is that you have a lot of them, and there is a lot of missions across the spectrum, and it's very important to add the results we get from either X-ray mission or UVIT mission to the existing data, so that you can actually combine the data to drive science. So it is important to disseminate the data. So these are famous tools which we see from the US, the MAST as well as HESARC. So the ISRO has also set it up at the ISSDC, and this is the Science Data Archive for AstroSat, and this is a screenshot from the archive. So you can see that these data are disseminated. It tells you with data for observation. It also tells you when the data is released. So these data, once it is released, anybody can download and start using the data. So it's extremely important, because data democratization has really changed astronomy, because it's not about producing data, but making it available in a usable form so that anybody can do research on it. So this has really changed, and now a number of people who are not originally part of the mission are using, and a number of students are also using it. So I stop here to take questions, and I request Pratik to take over.
Thank you, Annapurni. Everyone can hear me? Can you hear me?
Yeah, I can hear you. Yeah.
Okay, very good. So actually, thanks for providing that nice overview of AstroSat, and in particular UVIT, the instrument that you have been most closely associated with. So we have one question already. I actually encourage the participants to post their questions right now while we take this first question. So the first question is from Ravi Rajamani, who asks, UV does not reach the surface of the Earth, I thought UV is what we use filters in our glasses for. So it's a very logical question.
Yeah, so ultraviolet is a term which can be used, I mean, for a larger wavelength coverage. So if you even if you look have a VIBGYOR, whether the bluest part is something like we call it as an ultraviolet radiation, right? So it's closer to the UV, but whatever UV it leaks through our the closer to the blue is part we call is what we receive on Earth is called the ultraviolet for that purposes. But when you look at the electromagnetic spectrum, the ultraviolet range is too much bluer, or rather a shorter wavelengths. So we are looking at the wavelength region, which is not, which doesn't enter our Earth's atmosphere. So we do get the redder part or the bluer part of the optical spectrum, which is like we call it as the blue part. But that is where even that part is kind of difficult for us skin, and we take protection. So that is the ultraviolet we are talking about in terms of terrestrial. Yeah, hope it answers the question.
Yeah. So basically the UV that we sort of refer to in our glasses, like UV protection, UV shield, is not really the UV that UVIT is sent up there in space to observe. It's sort of somewhat towards the optical side. I do not see any other questions. So just to sort of continue a discussion a little bit more, I just sort of wanted to ask myself, and maybe this will prompt others to ask a few more questions. So how big is this whole assembled AstroSat instrument in space, like, in terms of dimensions?
This should be a few meters, 5 meters or so. So it's fairly big.
So
Yeah.
it's basically like
You can see the people sitting there, so you can actually have an idea of how big it is.
So
And
basically like
also
two people tall,
yeah,
roughly
yeah.
speaking. And it's almost a cube in shape.
Yeah. So you have all these instruments packed together. It's like a kind of a cube, and you also have star sensors to sense the direction in which it is looking at the sky, along with the other peripherals like the mission requirements and the solar panels. So if you just open like this, it's like you can see this particular picture. It's it's the it's a design. So it's like the wings on a cube.
So basically, when we're launching, it's all closed, and
It's
once
all closed, and
the
once it
the
right
power,
it
the
opens
solar
up.
panels. Okay, we have another question from Ramaswamy Krishnan, who asks, what was the science objective of observing UV, and the conclusion or findings to date in simple layperson terms? Were the objectives achieved?
Yes, so I will talk about a few objectives and talk about it in my presentation. But the objectives, one of the objectives is to have looking up at the sky together it in one direction is to look at any object which is going through an emission from very high energy to up to visible. So like from a hard X-ray up to visible. So you're looking at an object which is which can emit in all this wavelengths, and also some physical processes which are very difficult to answer without a simultaneous coverage. So you can have variability studies like the AGNs or X-ray, the binaries with black holes and as one of the components, or central regions of active galaxies. So these actually go through very erratic and not very clearly understood processes, which demand a co-observation with across the wavelength spectrum and with time variability. So simultaneous observation. So this was
that
one
also means, sorry to interrupt you. So that also means that all these instruments on board can really simultaneously observe the same object and study the physical nature of that object, right?
So that was one of the objectives. So that is met in terms of certain kind of objects which demand that. and also objects where you can actually individually study them, or two instruments together.
Okay.
Study
So
it,
anyway, you're
etc.
going to talk about the UV a little more in the remaining part of your talk.
Yes.
So, I think we can take this question to be answered. So then we have, so I don't quite understand. There's another question. Do we need continuous population to control the telescope? I think that what this means is, do you really need continuous monitoring by dedicated set of scientists to like make sure everything is working fine?
Yeah, so there are two types of monitoring. One is to monitor the mission as such, like the satellite, whether it is in the same orbit, or everything with respect to the electronics, the mechanical systems, everything is working fine. And second is the each and every instrument is working fine. So the instrument teams have their own payload operation centers where the data gets dumped, and they monitor whether the instrument is working fine, their health is fine, the temperature is fine, their electronics is working fine, etc., etc. But the mission takes care of the mission-related activities, like the satellite. Is it drifting? Is it in the orbit? Is it pointing well, etc., etc.
Basically, it has to be continuously monitored
It's
both for
monitored.
operations and for science.
Yeah, so you have very intense monitoring in the initial stages to understand the system, and then you have kind of, we settle down into a routine kind of a thing where you check everything, but you get red flags when there is off the limit. Till then, you can actually kind of eavesdrop into it and then keep monitoring. But if there's any change in object, then the mission has to little pay attention to make sure that it reaches the object. Yeah.
Okay, very good. So Gyan N asks, what is the role of private sector in this? How the private sector uh, involvement is coming up in this space in India?
Yeah, so when you look at this mission, for that matter, the requirements, the specifications are put out by the scientists, and the engineers actually design it. So we get the design done within, but then we are not manufacturers. We don't manufacture anything. So all these components do get manufactured only in the industry. So what I meant by Make in India is that these are all done in the country, within the country. All the components, though the specifications are given to them what to manufacture, but then they're all manufactured within the country, except very specific critical components. So that's where the industry come in.
So there is a very close involvement of
Yeah.
in making almost all
of this. Yeah, we don't have manufacturing capabilities, right? So we do get these components. We have the designing capabilities. We get it. The industry manufactures it. In sometimes they even do the modeling, like thermal modeling to certain detailed things. We had outsourced to certain engineering companies, and we get it back, and then we integrate it. That capability is there. So capability of integration of what we get, and then testing finally. That is at in-house, but the industry manufactures the components.
Okay, very good. So we have an anonymous question. What are the steps between the observation and releasing the data? It looks like there is a fairly large time gap. So basically data availability.
Right. So what basically means is that we, as we did the component testing ground, we put together and integrated. You will not be able to do all the testing on ground. So you have to list out the testing which has to be performed in space, and then combine everything to actually make the performances, like the table which I mentioned in the beginning. I have to make sure that each items are ticked off and which are within the parameters. So that has to be published to make sure that that we have achieved what we set out for. So it takes a bit of time, and then normally the performance verification phase, which is assigned to each mission, is assigned to carry out all these kind of activities. And these are piecemeal activities where you combine to get a file which clearly says what it is, and it is used to convert the observed image into a science-ready image. So at least 6 months it takes. And also that you also have to optimize certain things which you might encounter in the process. So eventually you optimize and give it to the user that this is the way you operate the instrument to get best benefits out of it. And this is the way you process the data, it comes out, and then deposit it. So it takes about 6 to 8 months to get a maturity in this, so that we are not putting out any, garbage out.
Okay, so basically you're very careful before like putting out the data. You don't want to like say, oh no, that was not right. Maybe
Correct,
this.
correct.
So you
So
just
we
want to be sure.
fairly certain we will put it out, but then the modifications to a certain 1 or 2% gets done in a couple of years' time. So yeah.
Okay, it's already 5:40, 40 minutes past the hour. We should actually continue with the presentation, and we'll take the remaining and more questions after the talk ends. Annapurni, please go ahead.
Yeah, thank you. Yeah, so my science questions were to look at the certain types of stars which are very hot, basically because they're either the core is bare or they are towards the end of their lifetime, or they are very big and bright and they're very hot and they emit a lot of their light in the ultraviolet. So that kind of stars you can see in several systems, like the groups of stars, like the open clusters, which are like the loose groups of stars which we see in our galaxy and also other galaxies, but they get very faint when you go out to external galaxies. The global that they are the open clusters, like our Kritika or Pleiades, Hyades, which are up in the sky, easy to observe with eye. Globular clusters are very densely packed system of stars, which very large number of stars in a small volume. Omega Centauri is one of the very massive cluster, which can be visible with a small telescope, or even in good sky conditions you can see it naked eye. And there are OB associations, like in the Orion cluster, you can see them. They're very bright stars and massive stars, and they also emit a lot of ultraviolet emission. Now, why do you need to study the ultraviolet emission? You can see them very clearly in the optical images, which is shown here. So why are you taking trouble to actually go and observe in the ultraviolet? It's because this ultraviolet emission plays a major role in the case of formation of stars, as well as dissipating the material, because these high energy photons, which are in the ultraviolet, actually ionizes the material around these OB associations, or most of the star formation regions in this NGC 300, 1300 spiral arms. So the ionization and the you can see these pink dots where they are completely the gas is completely ionized. So the ultraviolet rays plays a major role in ionization. And in globular cluster and open cluster, the death of stars, like the sun-like stars, when they die, how do they die? And also in the case of globular clusters, we know that the stars literally collide. This is one of the very special systems where stars can actually collide. And there are various types of new types of stars which are formed, which are not actually seen in systems which don't collide. So how do collision take place? And this is mainly happens in the central regions of these clusters. And there's a zoo of various types of stars in the center. And dramatically in the ultraviolet, the crowding reduces, because it's like all of them emit like the sun. And when you look at the ultraviolet, most of them are very dim, except the hot stars. So it's like you are trying to detect a firefly in the middle of a floodlight. You just switch off the floodlight, you will see the firefly. So it's like that. So ultraviolet is like the switching of the floodlight, because it kind of filters out all the optical light. So my interest is in these kind of objects. So I kind of the scientific aim is to understand the late stages of stars as well as the early massive stars. So these are like what we do in astronomy is like we put out the plot the luminosity against temperature, and they form a nice sequence of stars, which is called the main sequence stars, where the stars burn their the fuse hydrogen in the center like the sun, and then when they exhaust the core hydrogen and they become helium, they kind of expand to become red giants. But I'm also interested in the right picture you see. There are some stars which defy this stellar evolution, and they continue to live on the main sequence, meaning that they stay young and they refuse to grow old. And these are called blue stragglers. And I conducted a lot of studies using this. I'll come to it in a while. And star clusters are very important because they actually help us to understand the evolution of stars, because they actually have a kind of a pattern, and then based on this turn-off, you can actually identify the age of the cluster, which also tells you how much time a star stays on the phase of fusing hydrogen at the center, and when do they become red giants, where you have an inert helium core, etc., and then it becomes a red giant, etc. So I've been working on star clusters to understand the evolution of stars for a very long time, and hence I'm interested in understanding the various evolutionary stages. Like what happens after red giant? Do they all go to different evolutionary phases? How do they transfer to become white dwarfs, where they just basically shrink and condense and cool off? So these are various things which I'm trying to address. And what happens, how do the stars behave when you have a binary, like two stars together, and how do they evolve? And they also open up a lot of avenues which are past the normal standard evolution, standard stellar evolution. So this is the color magnitude diagram of a globular cluster. Color magnitude diagram would mean that color on the x-axis, which is equivalent to a physical entity, the temperature, surface temperature. The magnitude is nothing but the luminosity. So you can see that the stars which are shown as blue stragglers are stars which are actually avoided evolution, and they are hot, and you can actually observe them in the ultraviolet because they're hotter than about 6,000, 7,000. And these are horizontal branch stars, which are actually co-helium burning stars, where instead of hydrogen fusing, they have helium fusing. So it's like the later evolutionary stages, and they are the potential stars to become white dwarfs. Now, we do not understand how the evolution proceeds because they are mostly near the core of the cluster, and you can't figure them out in this crowded field. And this is the way in which the spectral distribution is there. We call this as the black body radiation. And the hotter the stars, they emit more in the ultraviolet. So I'm interested in the flux in the ultraviolet, which will tell me the hotter ones. So this is a kind of a cartoon made by one of my previous PhD students, Snehalata. And so this is like, okay, there are stars which are younger, like the one I showed here. And previously people thought that they are kind of, you're taken something from the background. They're not part of the cluster, so they're not a member of a family. But then later studies said that, yes, they are part of the family. And in fact, they actually have all the properties and they are having the same motion. So it's part of the things. How are they able to continue in the same main sequence, evading the evolution? Then the only reason is they could have got extra fuel. And how can you get an extra fuel? You can either collide with one and then become a more massive star, or you actually eat up matter from a companion. It's called a vampire star. And you can become the star, the one which kind of ate up can become a more massive one. Or you can also kind of in triple systems, stars could be born in triples or in binaries in groups of, like in these clusters. And triple systems also, the inner binary can actually either merge in a slow process or become this kind of a mass transfer process where the mass transfer can happen. So these are three mechanisms for extra fuel. But this is theoretically done, so we have to figure out which one actually happens. And so this is one of the things which I pursued, and Sneha's work is also part of it. And this is mentioned here, the difference being the collisional product or the merger product will result only in one star. There won't be any companion. But if there's any mass transfer, then you have a companion, which is a white dwarf. And as you saw in this previous plot, if you have a white dwarf, it'll be over here, which would mean that it is actually hot and you can actually detect in the ultraviolet. So the idea was to detect them in the ultraviolet and a hot companion. If they have, then it would mean that this is the pathway it has taken. And depends on when this mass transfer happens, you can have a very small white dwarf to a massive white dwarf. So these are different mechanisms we know of. And this can happen like, there are two stars, A and B. And when the A becomes bigger, the mass gets transferred to B, the B gains mass and it becomes a blue straggler, and the A ends up its life as a white dwarf, and this is called blue straggler. But there's also a process where within the main sequence itself, it can happen and the B never comes out, and it is actually masquerading as a normal star within the main sequence itself. So you can still have blue lurkers. So there's another term, and we have discovered these blue lurkers, and we believe that the systems are present in the groups of stars which we're studying. So these are the kind of things which you have done, and these are we never expected this blue lurker to be there, but then we got them as well. But I'm explaining both the processes, but we set out thinking that this is possible to detect the blue straggler. So that was the main thing. This was not part of the initial studies, but then the first paper which was the first author, which we published within the first year of the door opening, was the discovery of a companion to a blue straggler in a cluster. So which actually opened up a lot of avenues that we can discover such binary systems. And this was really an eye-opener, and we discovered this, and then this was the first result. And as I put it as vampire star, because it is a way it can relate to what we know. And this was this had a lot of media attraction in the first result. Since then, we carried out several studies of clusters, particularly to find out the binaries and different types of binaries and different stages of evolution. It's called blue stragglers, yellow stragglers, horizontal branch stars, sub-dwarfs, white dwarfs, planetary nebulae, etc. And we have carried out about 14 clusters so far. And this is a series we started with UVIT Open Cluster study. And it's got about 16 publications now, and there are several PhD students have completed their PhDs on this topic, and several other students who did their master's project or internship project, etc. And so this is the first one where we had one of the nearby clusters called M67. This is an important cluster because it's at about 1 kiloparsec, and this cluster has a similar the metal content and the age as our sun. So there are several sun-like stars in this cluster, and we study the solar twin phenomena and how is our sun can be, I mean, how is it performing with respect to the sun-like stars? So several studies are carried out here. And in this case also, we find systems where this blue axis over here, you can see this is the observed data points, and this is the observed spectrum. It fits well in the first two ones. The third one, you can see that the observed expected flux drops down, but the observed flux continues, and you need another component to fix it, and it happens to be a stripped core of a normal star. And there's another technique which we use called the seismology technique, which is astroseismology. Helioseismology is very well known now because the sun also pulsates, and we study the waves on the surface of the sun, and we actually understand how the interior of the sun is working. Similarly, can be applied to stars, and so we wanted to understand if you have a system which is actually having an axis and which is actually a system where it is actually has acquired material. So if the star acquires material, how is its internal physics different from a normal star? So you need to understand the pulsation within that star to understand, does it pulsate like a normal star or the pulsation different? So can we probe the interior of this post-mass transfer system? That's a blue straggler. So we used a Kepler mission and TESS mission, which actually looks at the variability of the star, which tells you that these are the modes in which it is pulsating. This is actually a delta Scuti star, where it actually belonging to a pulsating variable. And we got this light curve, which would mean that you can see this light curve, which would mean that it is actually pulsating, but this is not a sinusoidal pulsation. There is a variation here. And this is also because it is not actually called eclipses. These, when two stars go around each other, you get an eclipse. But here it is actually a ellipsoidal variation. One of the star is actually distorted because of the white dwarf, and it is giving rise to these kind of effects. And what we see is that this blue straggler is a normal star, but it has got a companion which is of its mass is 0.2, which is like the core of our sun. So that the mass of the core of a sun will be like about 0.2, 20%. So this is like a stripped core, and this gave us an idea about the internal mechanisms of this blue straggler. And this is the same as we got it from the SET previous study. So this gives us understanding of the evolution or how the star works. Here is the planetary nebula. So this is a picture of the cluster, and this is the planetary nebula. Planetary nebula is actually how a sun-like star would die. And you would expect that, everyone expected that, since a cluster with stars like the sun, you would actually see many of this death of the stars and the the white dwarfs you do see, but planetary nebula we don't see. It's like the transition from a star to a white dwarf. The transition works very fast that we can't see how it transits, and planetary nebula in a cluster is a very rare phenomenon. And 2818 is a cluster which has got a planetary nebula with the same name. So we observed that with UVIT, and you can see nice nebula around it. So this is actually the outer envelope of a star which is being lifted, so it's getting ionized. And the ultraviolet radiation is coming because the highly ionized high temperature gas is out there, and this is the structure we get. And we model everything, and then we find that actually this is star could be evolved from this cluster. So we are actually seeing the death of a star in the process through a planetary nebula in this cluster, which is very unique. And we know only of a couple of one or two such examples in our galaxy. Moving forward, we do see very large number of these objects which are evading the stellar evolution. And all these objects are blue stragglers. When we actually find out their partners or the companions, you expect all of them to sit here. These are the white dwarf areas. But we do see many of them in this area, which is actually a gap area. You see these lines, these are the white dwarf tracks. So the region which I showed earlier, the white dwarfs are expected to be here, and the main sequence stars which are burning, fusing hydrogen at the center is here. And this is a gap area. They're called stars in this area are called gap, and you don't actually find normal stellar evolution to populate this area. But we have seen that many of the stars are populating in this area, which would mean that only binary systems or mass transfer systems can fall in here. So we see in many clusters this gap area being filled up. We do see some over here, which are basically like the sub-dwarfs. So these are low mass white dwarfs. So we have found many such systems which are through this gap, and most of them are coming from the companions over here. So the conclusion, or rather the impact, is that we actually able to find the pathways of formation of these systems which were never understood earlier. We all postulated that it could be due to binary, but there was no direct evidence. But here are the direct evidence to show that this gap area gets filled up by this systems and binaries. But where will they end will depend on what kind of a system it is going through, what kind of a binary it is, what kind of a initial mass they have, and when the mass transfer takes place will decide on which part of the this diagram it falls in, because it has got a different temperature, it's got different size, etc. So this is a very eye-opener for us. And we also see now many of the pulsating stars, and we actually validate what we see from our observations with the actual pulsations of the star to understand them. And so we have come to many discoveries. The recent ones these three are the recent ones. And I have one of the things which we've also done is that you have this technology transfer happening, but then here is basically we handle groups of people to actually take over that kind of an area and move on. So Kausha Vaidya from BITS Pilani and her team have been working with us, and we have trained them, and then they have taken over. And to the extent that we had 2 papers with the same number, you can see this both 14th publication. So 2 teams did not talk, and then the paper got accepted at a very similar time. So I'm happy to say that many people started working on this area and this technique, what we have developed to unearth the components, the binary components, and understand the impact of that in the stellar evolution. And we have another set of people who are in Guwahati University. They are also trying to do this. So this is expanding, and since a lot of data is also available, but my team is also moving to another direction to find out how the chemistry is changing. Can you detect a surface chemistry difference? And we see some chemistry difference in some of the stars in M67. And that is basically because of the pro-system material coming in. So we are working on it. And this is a paper where we first detected highly barium element, which is actually a pro-system material on a blue straggler, which has got a white dwarf companion. So you can clearly see that white dwarf in its previous, when it was a star, it processed the material and transferred it to the blue straggler. And that is we are actually filling the gap of that evolutionary sequence in this. Moving on to the Globular Cluster Survey, we have done a number of publications with that. And 11 clusters have studied so far when we published a couple of years ago. And the large number of student team is involved in it, where 3 PhDs have come out and there are 4 more PhD students on collaboration. So the problem with this thing is that we had to work with the modeling team quite a bit, because when the models were there, when we initially compared, they were not matching at all. And we had to work with the modeling team to basically adjust the parameters so that it can meet or it can fit the observations. And we have a lot of different types of studies involved here. And this is the kind of collage we have. So as I mentioned, you can see on the right, the optical images of these globular clusters. They're very dense. There are too many stars out there. And but if you see the ultraviolet images that are on the far UV, there are not too many stars out there at all. So we are actually picking up all the hot stars. And even in some of the cases, we can go very close to the center to figure out what exactly is happening. And that is helping us to discover systems which otherwise is not known. So that has really helped us. And so this is the combined diagram. So if you look at the lower plot, that was what was available 10 years ago. But with the increased understanding or information on membership and cleaning up, we can actually see the pattern of the core helium burning star. These are the blue stragglers, and these are stars which are evolving off and coming onto the white dwarf sequence. So we were not we did not have an understanding of how many of these hot stars are present and how they evolve and what are their structures. So this study has actually helped us to discover them. And so in the case of blue stragglers and globular clusters, as I mentioned, you can actually collide and make binaries or single stars. The collision process is a major thing in globular clusters, because you can see that the crowding is too much. So in the centers, you actually can have collision. In the case of open clusters, the blue stragglers are mainly formed from mass transfer. Here, the collisions play roles, but we were able to, for the first time, differentiate between collisional products and mass transfer products. The blue are likely to be collisions. We also don't detect them. They're hotter and bluer and luminous, and these are the mass transfer products. We also detect their white dwarf companions, and they separate them on this plot as well. But on the other hand, we do see some of them in the outskirts also. So, but they are binaries. So there is a collision process in the inside, but there is also binary process in the outside place. And they are on the main sequence itself. And this cluster is particularly important because dynamics-wise, the globular clusters are known to have something called core collapse. And that's a dynamical thing, which I can explain if anybody is interested. But this cluster has gone through this core collapse, and the binary formation is the only way in which you can save everything collapsing to become a black hole or something. So we do see the evidence of binary formation here. And we do have different studies of bright stellar population, and particularly these stars which are very hot, which are coming from the centers, are also either are binary products, and some of them could be collisional products as well, so which you are able to see it. I would like to stop by introducing one more topic on galaxies. I thought it'd be nice to touch upon it. We also have carried out studies of galaxies which have merged a few 100 million years ago, and you can see the tidal tails, long tidal tails, and there is star formation in this tidal tail. So this is the Atoms of Peace galaxy, and this first study was led by Koshi George. And these star formation actually, you can study how this tidal, the matter which is actually taken out of the galaxy, but they cool down and make star formation and make small structures. How is it formed? So, and details we studied. But also this galaxy has actually got a UV depletion at the center, which actually points to an Aegean and suppression of star formation. So activity within the galaxy as well as outside the galaxy was brought out very clearly. There's another area where we've been working with Koshi also is the jellyfish galaxies. They are a new group of galaxies which came to astronomers' attention a decade ago. And these are like jellyfish, look like jellyfish. The gas gets stripped out of them when they move through clusters of galaxies. And then a nice picture of this jellyfish galaxy. It's falling into this kind of a cluster, and this you can see the lobe-sided the star formation, and it's stripped of a lot of gas. Again, there is a depletion of UV at the center, which is basically the star formation is stopped. And the several publications have come up. A couple of publications we did earlier, and then we continue again with in the last couple of years, and we are continuing. So basically, these are the kind of galaxy, very good resolution of UVIT is helping us actually. The NASA mission Galaxy is not able to see this. So you can see these kind of stretches, and we combine with the H alpha, which is the tracer of star formation. So the tails of confirmed cluster member galaxies are found to be oriented away from the cluster center. Basically means that the gas is being tidally stripped away, or ram pressure stripping is happening. There's a significant star formation in the strip tails and the suppressed star formation in the central regions. Many of them, you can see that the star formation is stripped. And there's a possible case of accelerated quenching happening in these galaxies. So this is the kind of, there's another paper we are working on with a large number of observations and groups. So yeah, thank you for your attention. I'm ready to take questions. Yeah, over to you, Pratik.
Yeah, thank you, Annapurni. So we have some time for questions. So in the second half, you mostly talked about the UVIT results, particularly the ones that you were involved with. So if you have questions about that or related things, please post them in the chat box. So from the last time, we have a few questions, but I'll actually go to this question. There's an anonymous attendee who says, I thought IR is hot, not UV. So basically, that's his confusion. He says that infrared is supposed to be hot. You have infrared imagers and so on, which detects things which are sort of warm. So, but why is UV hotter than IR?
Yeah, the energy of an UV photon is higher than the energy of a infrared photon. So that way it is hotter. But then in the sense that you're looking at warmer, you look at IR, not hotter. And any gas environment or things like that. It's like our body is warm, we emit an infrared.
So yeah, basically, I think it's sort of this question arises from this thermal imaging in IR, right? You know, if you go to these science exhibitions and so on, and you see, oh, there is this our body sort of emitting.
Yeah.
And so that's, I think, the origin of this question. So yeah, IR is warm, but not as hot as UV.
Blue and yeah, it gets hotter towards the blue and yeah.
Towards the shorter wavelengths.
And X-ray, you go to gamma, you actually burn your the tissues get burned as such, right? So.
Okay, so please post your questions from the last time. There are a few remaining questions. So Ravi Rajamani asks, what kind of propulsion system was used to launch AstroSat?
It's still the PSLV, so whatever propulsion is used in PSLV is the same thing. But in AstroSat, you also have each payload has its own fuel as well. I'm not sure what exactly the fuel is, but then the fuel is used to for the momentum dumping, for reorienting, etc. There is fuel in the satellite itself. So depending upon the availability of fuel, the mission lifetime gets decided as well. It's one of the factors to decide the lifetime of that mission. There is fuel on board, but I don't know exactly what fuel is used.
So then there is a question from Ramaswamy Krishnan. The question is the satellite pointed at specific parts of the sky where specific objects are known to exist, or do you scan different parts looking for emitting objects?
Yeah, so this is the, like, this is, we have pointed, this is an image of, let me, it's about 10 minutes image. We have pointed out to this galaxy. Sorry. Yeah, so this galaxy called NGC 2336. So we point in that direction and you get this image. And then you have to do the post-processing to get the actual image. So you are pointing, you're not scanning. It's just pointing and shooting and integrating over time, whatever exposure time is required.
Right. So
Yeah.
it's not a very wide field of view. So you have a smaller.
It's fairly wide field of view. Actually, it's about 20 dark minute.
Okay.
Half a degree field, yeah.
But it's sort of not like the whole sky is visible or something like that.
No, that is fish, like you get a fisheye lens, right? So
Yeah.
you won't get resolution. So if you want to have high resolution, you would get into, you kind of gets pencil beam kind of a thing, and it becomes very small field of view. This is a fairly large field of view, and you get large number of objects within the sky.
Right.
Yeah.
So people also study simultaneously different objects in the same field of view as well.
Yeah. So if I want to show you this cluster, like this is actually this is a picture of a cluster where you have the planetary nebula and the stars, etc. Right? So this is fairly big. You're not looking at only this and doing it. This is like about half an arc minute. So this is like 1 arc minute. And these images which we have shown here, they are all not very big. You have a lot of them as well. So let me go to the very first slide which I used. I'll just let me quickly go to it. So I just want to point out something else because it's related to the question. So you can actually see this one of the clusters. I think it's 2298, and you can actually see this is a small galaxy out here.
So both of them can be studied.
Yeah, so you can study them. You can clearly see the spiral arms very, very nicely, clearly visible, focused. And you can see another galaxy out here. So there are many things which are in the background. You get to see a study along with it. And within this cluster itself, you can see a couple of galaxies in the background. Yeah.
Okay, very good. So we have some more questions now. So there is a question. Have you found a new star named after you or your partners? It's sort of like, is there a new star that UVIT has discovered?
Yeah, we have discovered a lot of new stars in the sense that they're all partners. Yeah. But there are discoveries of galaxies. There's a recent one which is formed in the tidal galaxy, but there's another one which was actually too faint. But when we picked it up in UE, because it's a lot of some bright stars were there, and there was a couple of discoveries of galaxies. But we do have discovery of a lot of these new stars.
Right.
We don't normally name them specifically, but we list it out in the catalog. Yeah.
And there are a lot of stars. So
Yeah.
Yeah. So very good. So how far back in time, so this is from Sushila Venkatraman, how far back in time have you been able to observe?
Okay, so these are local universe because this is within the galaxy. I'm not going out beyond the galaxy because these are individual stars. So if you go to these galaxies, they are slightly far away. And also we should remember that if you go very far, then they get redshifted and you won't get them much of the ultraviolet radiation. It gets redshifted to the visible and infrared, etc. Like the JWST, the James Webb, which is observing. Many of these emissions which we see are actually ultraviolet emission, which is redshifted to infrared. So it's observing in the infrared. So we can go up to Z of a redshift of 2 or 3. So the discovery of some galaxies, the cosmic noon, which are being published by Kanak Saha. So they are in that range. But these galaxies are not very far, but then then only we detect them in the ultraviolet. Yeah.
So the objects that you talked about, the clusters and so on, are within our galaxy or nearby. But AstroSat and UVIT also has sort of seen stars, stellar systems out to redshift of 2, which is when
Yeah. So these kind of galaxies are quite, far, and these are like these are basically OB type stars, like very massive stars forming in the outskirts of the galaxies. So what we trace here in the far ultraviolet is the very massive stars. These white dwarfs become very faint. You can't detect them, but only the massive stars are seen. and these are the massive stars. We basically trace the massive star population in the faraway galaxies.
Right. So there is also a little bit, there is some other question. Let me try to frame it. Can very high energy gamma rays travel slower in vacuum? As conjectured by magic telescope experiments. So can very high energy gamma rays travel slower in vacuum? So this is, and this is talking about greater than 250 GeV. So I think it's talking about some recent result where they claim that the gamma rays travel slower in vacuum compared to in space. Is that, I think that's the sense of this question. And then he says, is it evidence for quantum foam? It's a 2009 experiment. So I don't, yeah, I mean, if you want to answer this, you can, but I don't think this is a confirmed or, 100% established result, I would say.
Yeah, no, I don't know much about it, and I don't want to comment on it. Yes, yeah.
Right. Let's see. So I think we have answered all the questions in the chat box, but I can actually ask a few more. That is, so you were talking about these very exciting things like blue stragglers and stars actually physically colliding.
Yeah.
These, when were these? Are we like sure about? Have we really seen such a collision in the act, or are we just sort of inferring that this happened? That's how you got these blue stragglers, at least some types of those blue stragglers.
No, we don't. We can't. We haven't seen anything in action, or rather, we haven't caught anything red-handed like in violent collision.
Sure.
But then things like
extremely
the
rare,
smoking
right?
gun, yeah, the smoking gun of mass transfer is this. Like people have seen stars with barium. They knew that the stars which are like the sun cannot have produced barium because it's very heavy element, and only massive stars or stars in the later evolutionary stage can only produce it. So if a star like a sun shows barium, then it is actually borrowed from someone else. So, but there you wouldn't know from whom it is borrowed, right? Because you haven't seen the companion. So here we actually see the companion and the barium together. So that's a smoking gun of mass transfer. But collation, it is difficult, very difficult. And
it's difficult to tell apart collisions from binary mass transfer.
yeah, so that is where here is a cluster where it's of high potential, where you can actually see that there is a distinction between blue stragglers formed through collision and mass transfer. The models do predict it, and we actually are observing the same. But then what does it mean to the structure of the star? Like if two stars collide and merge, what does it mean? How is there any impact on the structure of the star versus the mass just flowing into a star? So that is where we are looking at the oscillations and astroseismology to understand the internal structure of the stars. But still, we haven't found a case where yes, it is a collisional product, and we can actually say that this system is produced by collision against this smoking gun of a mass transfer, which is a binary formation pathway. We haven't reached there yet, but we are trying our best to figure out the method by which we can use it, but not there. Yeah.
So basically, you've populated the color, magnitude, the luminosity, temperature diagram enough that you're sort of finding all these interesting systems in unexpected places, which will tell us how this process, from a planetary nebula to the white dwarf and these binary processes.
So in this case, if you can see the binary companions of this blue, the red ones over here, they are supposed to be here by this line, this blue line. They cannot come inside because this is the gap area. But all of them are falling in the gap area.
Okay. So I think as a follow-up of that question on gamma ray 250 GeV electrons, so Umesh Chandra has pointed out to paper, which I'll actually have a look at. But I'm actually, and I think also Annapurni are not aware of this. Is somewhat beyond this topic as well. Any other questions? So, I think we have a, few more minutes. So maybe I can actually move away a little bit from the science results to also like, you are also a very, you're also in science administration, and you have sort of played a role in, building and help build this UVIT telescope. You have, mentored a lot of students. So you have, played many roles, and all of them very well, and the results are showing. So maybe you can share some sort of insights, and especially for women scientists who, there are not a lot of women scientists in leadership positions, and there are various factors for this, but maybe you can say something about, like, how should women, how is it that women can make it, even in, of course, they are doing great science, but also, take up leadership positions. Maybe this is a question that you can answer.
Yeah, so actually, the Institute of Astrophysics, we do have a good number of women scientists. And when I started working, and I had spent a lot of time in the observatory Galactic while doing my PhD time. So it was not the kind of a foreign to me that when you go to an observatory, you feel alone. But there are women who spend time there and observing and do instrumentation there. So it was not something which was unusual for me to take up. But then when it comes to space engineering, and when you actually integrate it, in the UVIT team, there are not too many women involved. And but you just have to do whatever you're supposed to do and just move forward. And I think at the end of the day, your hard work and your whatever you innovatively think works. But at times it is not enough. You need to make sure that people do listen to you, people do acknowledge what is being done, and that I feel that some extra mile needs to be run compared to other people. But I think the system is much better now compared to 2 decades ago, and we do see that in conferences, meetings, and even in it's not panels anymore. We do have women representation in panels and committees, and it's very important because sometimes it's an subconscious bias. We're not even aware of that there is bias going on, but sometimes you get really comfortable with some way you take the decision. So you need to stop it and think and say that no, if there's a candidate, a woman and a man, you have to put them on the same footing and grade them. And at times there are situations where the woman is running multiple lanes. So you need to acknowledge that. And I'm not saying discount, but at least make it flexible so that they can come back and do the activities. So as far as astronomy is concerned, I think it is great because the data democratization has really helped, and you can do the data reductions or computations or simulations at wherever you are, and not necessarily at the desk attending to the work. So my PhD students, many of them have taken maternity leave and then but completed their PhD and the papers, and they've moved on to do PhD and continued in academia. So that's very heartening. Earlier it was not very easy, but I still think that more supportive environment is required and some amount of mentoring, because there are many times at crossroads where we don't know what to do. And I've seen women who tend to drop out instead of trying to somehow solve it and move on, pull on. So that kind of support and assurance that it's all right, you can just go slow, but you can tide over your hurdle and then move on, but don't drop out. Don't say no to it, don't quit. So quitting should not be an option at any point. then only you can get this women workforce back, and then women leaders and women, scientists. Yeah.
Thanks for answering that. And it's heartening to see that the situation is improving. So I think we are already 25 minutes after 6. I would actually invite Professor Abha Mishra to conclude the session. Abha.
Thank you. Thank you, Professor Annapurni, and thank you, Pratik. This is really wonderful webinar, and I think I also like when Pratik brought up this question about the how women are feeling and being you as the leading point. I'm sure that it's really kind of very motivational for others to listen and really follow the path to achieve certain milestones. I think this was wonderful evening, especially for me. Like morning, I started teaching my daughter who's in third standard and talking about the how things happen in space, and in the evening I really learned a lot to what it goes in getting those information. It's really wonderful. So this is means what we get to learn is this a long journey towards where we are at the global stage. This is really I think the amazing information what you have given, and especially when we got to learn that okay, how to work in Ladakh, working in Bangalore, how to operate, and so nothing can stop when you are really motivated and you really want to achieve things. This is really incredible things to know, and what goes into these means looking inside into this the powerful telescopes. This was like dissecting this means we always have seen these results in beautiful pictures, and what it takes to get, and what kind of calibration, what kind of the optimization you require. This was wonderful in your first part, and especially talking a lot of science coming from the director of an institution. For me it was like mind blowing. I it's really great talk today, and of course the science part was incredibly rich in and with the recent publications which you mentioned, and I think the Pratik has brought this conversation, and also along with the audience who were asking a lot of means, especially the information about the which wavelength is hotter. So so I think we had all kinds of the information filled today with this webinar, and I'm really grateful that you both of you spent time for this webinar. And so this webinar will be put in our YouTube channel, so this will be available to the audiences who missed today, and the whole information will be available online, so they may contact you directly. And I think one of my colleagues were saying that I'm going to speak to Professor Annapurni and see that how things are really working, and then take some course. So I say, okay, yes, of course you should. So yes, so with this, I would like to end the webinar here, and thanking both of you for your time and this wonderful talk and the discussion. And thank you, Professor Narayan, also being here. And so we meet sometime. So,
Yeah.
so Professor Narayan is driving back
Yeah,
home.
yeah. Yes. Very
So,
good. Yeah.
so very good evening, everybody. Thank
Yeah.
you. Bye.
Thank you. Bye-bye.
Yeah.